Okay, so today we're going to continue our discussion about convolutional neural networks. There was one slide we skipped over last time, and I want to return to, and it was on activations. So previously we saw that the ReLU activation is really important when you have a deep network in this compared to like a sigmoid or tanh, because the slope is 1 for all these positive inputs, and that allows you to avoid the vanishing gradient problem that you tend to get with sigmoids, because in a sigmoid, the slope is 1 only at the origin here, and then as you go away from the origin, the slope gets shallow, and then when that happens for layer after layer after layer, eventually the slopes get so small that the gradients vanish, and you don't train the early layers. So that was kind of the big innovation with the ReLU when it was introduced, I believe in the AlexNet in 2012. Okay, so the ReLU works great, but maybe it's not perfect. So one of the things that you can sometimes find after you've trained a deep network is that if you look at certain nodes in the network, that you find some of them are always 0 for all samples. So somehow they're just like stuck outputting 0. It's because somehow the outputs, what the signal going into that ReLU is negative always, and then the output is 0 always. So in some sense, that's a wasted neuron. It's not doing anything good for you. So one way to prevent that, and that's called the dead ReLU problem. So one way to prevent that is you add a tiny positive slope to the negative, to the left half of the ReLU, something like a slope of 0.01. And this is just enough so that there is a little bit of gradient that propagates here, and it helps to avoid the network just getting stuck, outputting zeros in all those nodes. So that's called a leaky ReLU. And it usually just works pretty well. I don't know of any real downsides to it. I think usually it works a bit better than the ReLU. And then there's a further advance called the parametric ReLU, which says, well, can't we just train the slope A? So maybe initializes it at 0.01, but then it allows that to be learned with all the other network parameters to see if it can come up with a different slope at every layer. Okay, so that's the parametric ReLU. It's usually a bit of an improvement on the leaky ReLU. But then it turns out that there's all these other activation functions that have been developed and promoted by their inventors. Some of them might help, some of them might not. Maybe some are application specific. But just to give you an example of one that's pretty well known now, it is the exponential linear unit. And so this one, when you look at what happens at the positive, for positive inputs, it behaves exactly like a ReLU. But then for negative inputs, instead of having this sharp edge and outputting zeros, it has a smoothly decaying shape that eventually flattens out. And so this smoothness here can help a lot with the optimization. It's a lot easier for optimization algorithms to handle that smooth shape. And let's see, so here there is a tunable parameter, alpha, and that tunable parameter will set, let's see, so if you look at what happens here, when z is very, very negative, large and negative, then this thing will go to 0, right? And so that means that minus alpha is the value here. So minus alpha. So you can set alpha, or maybe, I can't remember, maybe you can learn it. But if you choose a different alpha, maybe it does something like this, or has a sharper edge. But that's a free parameter in this scheme. And so, yeah, and then there's another one called the sigmoid, sigmoid linear unit that tends to work really well. People find when they put that in a network, like any of the networks that we talked about or we'll talk about today, just performance gets a little bit better across the board. So there's various of these ones people talk about, but just wanted to give you the flavor of a few of them. Okay. Any questions on activation functions? Yeah.
Can you repeat what you meant by like dead neurons?
The dead neurons? It's like when you, after you train a network and you just look at the outputs of the different activations, so call those neurons. So those are, if you look at what's coming out of the different neurons after it's trained, or coming out of the different activations, sometimes you find that some of those values are always 0, like no matter what, for any input. And so somehow when you train it just learned some pattern of weights that set them to 0. So they're kind of wasted. It's a wasted opportunity. Maybe the network could work better if that didn't happen. So that's the dead ReLU problem, and then these are some solutions to it. Okay. All right, any other questions? Okay. So, all right, so we talked about the demo. We talked about how things like batch norm and dropout and data augmentation tend to help. Although in this example, I'm not sure why data augmentation wasn't helping. Maybe I should revisit it, check to see what's going on there. So, what we're going to do today, and maybe the next time we don't finish it, is we're going to learn about other famous networks. We talked about AlexNet, but let's go in history, what happened the next year, to understand the advances that were made and the tricks that were developed to make these things better and better. And then let's talk about how we, as individuals, can actually benefit from all this through transfer learning. So the idea is that these networks that we've been talking about for ImageNet are gigantic. If you tried to train it yourself, probably is not going to be possible. It might take like a year on your computer, or some crazy, maybe longer. And so these are trained, at places like Google or Facebook that just have massive resources, and even there it might take them weeks to train one of these things. So they're giant. So we can't use them directly. However, what we can do is we can notice that often the early layers, and what we mean by that, like the first layers in the network, all the convolutional ones, so these are like the conv layers, are more or less universal. Like these things are just breaking down images into little pieces that are sort of, these little pieces, you can use them to classify any given class in ImageNet, or you can use them for many other things. And so those are things that we can just leave as they learned them. So first of all, you can download the entire trained network in PyTorch. I'll show you how to do that. Once you have that, you can just leave all the convolutional layers as is, but then you can revisit the dense layers, which is where the classification really happens. So if you want to do some new classification task, like, have you guys ever heard of hot dog, not hot dog? So there was a TV show. I can't remember which one. Oh, you know it.
Yeah.
What was the TV show?
Silicon Valley.
Silicon Valley, right. So there's this TV show, this is maybe like, 6-7 years ago, where it's kind of a joke on this. Somebody wanted to train a neural network to detect in a picture whether there was a hot dog or not a hot dog. And I can't remember the whole thing, but it was just this kind of funny thing they thought about doing. So it's like, yeah, you can definitely do that. So how would you do that? Well, you'd need to get a whole bunch of pictures of hot dogs, pictures without hot dogs. And then what you would do is you would relearn the dense layers in this new network. And obviously that last dense layer would just need to have one output, not 1,000. And that's something you can do. It's definitely fine, and that's something you will do in the lab for Unit 9. You can do like bicycles versus cars. And so you can basically take all these convolutional layers that are learned for you by Google or whoever, and then you learn your dense layer to do bicycles versus cars on your own data set. which we can download from Flickr or somewhere like that. And that's a tractable thing. You can actually do that, no problem on a laptop. So that's the idea behind transfer learning, is you're sort of transferring the knowledge from this pre-trained network to this new task. So that's this application we've discussed here. You only have enough data and maybe compute power to train a few layers, so you just train those convolutional ones. There's other things you can do with this idea. Those features that are learned by the convolutional layers are just useful for a lot of things. So I'll give you some examples. So if you want to talk about image quality, like if somebody gives you an image that was maybe compressed by some compression algorithm, or maybe it was distorted and you tried to undistort it or denoise it or do something, there's a fundamental question about how you measure the quality of that image. Like you can say, well, maybe I know the original image and I can measure the sum squared error between them, mean squared error. So that's certainly one way to do it. But if you do that, if you train a network to optimize that metric, you'll find that it gives you images that are just slightly blurry. They're not very sharp. They don't look like a great image. So the question is, well, how do you actually define what is a great looking image, or what's the right metric to take you from a ground truth and a reconstruction to a number that really represents, yes, this is a really great reconstruction or not. And so this is like a field that people have been working on for decades. And the best methods now, they all work by taking something like VGG16, which we'll talk about today, one of these early networks. You just take the convolutional layer outputs from that network, and you use them to represent the image. And they're much smaller than the image. They're sort of compressed, and they, in some sense, matter a lot more. And then you can compare, let's say, the original image's features to these images' features, maybe in something like mean squared error. And that ends up correlating much better with humans' perceptions of what quality really is in images. So that's just one example. There's all these things you can do with these features, because these features that are generated by those convolutional layers are usually a lot smaller than the number of pixels in the original image. In some sense, you've distilled things down to what matters, and then you can use them for other tasks. So, all right. So any questions about that? Yeah.
How transferable are these things? Like if it was trained on classifying things in photos, can we give it a table of medical test data and it'll do something with that? Or
yeah, I mean the answer is pretty much yes, they are. So in fact, I do some research on MRI, and there was recently, and MRI is one of these applications where it is difficult to say what does a radiologist want to see? Because they're going to make a diagnosis, and if the image is noisy and they can kind of see through the noise and still see what they need to see, that's what matters to them, right? So someone did a huge study with many radiologists and many images and many metrics, something like 50 different metrics for how you can measure quality. And the best approaches were based on taking the features from VGG16, which we'll talk about soon, and basically doing some relatively simple processing on those features. And VGG16 is trained on ImageNet, and we're applying it to medical images now. So there's some kind of interesting questions, because ImageNet is color, our medical images they're either grayscale or complex valued, so you have real and imaginary channels. So how do you take those two and put it into the three? Or but still, yes, it actually that of the 50 things they tried actually worked best. So it does seem like it is able to transfer, because there's just something about images that are kind of fundamental. Images and humans, what we want to see, what we can see in images. We see textures and edges and stuff, and if I give you two images and there's some noisy little texture, and I change those pixels randomly, and I ask you, can you tell a difference? No way, because it just looks like a rough patch, right? But if you measured the mean squared error difference between them, all those pixels would be completely different. It would light up as being a huge difference. That's a kind of example about how our visual system works different than mean squared error. Okay, but it's a good question. Any other questions on this? Okay, so these are different things we can do. Use a pre-trained network to generate features for a new learning task, or even a non-learning task, something like image quality quantification. And there's a bunch of other applications. If you want to read about them, this is a nice overview. Okay, so PyTorch gives you access to many of these famous models. So AlexNet, this is just going in the order of time when they were invented. So we talked about AlexNet. So we'll talk about VGG, GoogleNet, ResNet, Inception v3, DenseNet, SqueezeNet. And there's others. This is just what I could fit in this one line. And then we'll go through the demo also to see exactly how we can do this. So what we'll do next is we'll kind of go through in this order, in the time order, and understand how deep networks evolved, the tricks that they developed to get to where we are today. Okay, so VGG was, so if you remember AlexNet, I think that was 2012. So this network won some contests a couple years later, 2014. So generally speaking, all these networks had a few advances, but I'm just going to try to summarize what I think are the most major ones. So with VGG, one of the main ideas, main ways that they went beyond AlexNet or improved upon AlexNet, was to use very small kernels, but more layers. Okay, so when you think about AlexNet, if you remember the first layer in AlexNet used an 11 by 11 kernel, and now we're talking about using 3 by 3 kernels. Generally speaking, kernels are odd number by odd number because that way they have a center. And so like 3 by 3 is pretty much the smallest you can go, right? Before you have a trivial 1 pixel kernel, which doesn't do any spatial processing. So this is as small as you can go. And so obviously small kernels can't do as much, right? So that means you have to have more layers to really be able to do much filtering in the spatial domain. But this has kind of a hidden advantage in the sense that, like, let's say that I want to do, I want to implement an 11 by 11 convolution by an 11 by 11 kernel. So I can actually do that if I take 2 3 by 3 kernels. Well, let's just start there. Let's say I have 2 3 by 3 kernels. And what I'm doing here is I'm thinking of them. So maybe I have an image coming in, and I'm putting it through one convolution, and then I'm putting the result of that through another convolution, right? As you might remember from linear systems theory, you can think of this approach actually as, because these are linear, you can think of this as x is going into the convolution of these two linear systems. A new system, which is the impulse responses of those original two systems convolved. Does that sound familiar from 3050, 5200? So 2 linear systems cascaded, you can think of as a single linear system that is made from the impulse response of this convolved with the impulse response of this. And the impulse response of our convolutional system is just the kernel. Okay, so basically what we're saying is, imagine we take out all the activations for now. So we just have 2 linear layers. Let's say that each of them is a 3 by 3 kernel. What happens when I convolve 2 3 by 3 kernels? What do I get? 5 by 5, exactly. Now, that 5 by 5 kernel, you can't make every 5 by 5 kernel out of two of these, right? Because how many total parameters do we have here? 18. With a 5 by 5 kernel, how many total parameters? 25, right? So I can't make every 5 by 5 kernel by convolving 2 3 by 3 kernels. But I can make some subset of them, some subspace of them. And so this, so if I do this twice, I get a 5 by 5. If I do this 5 times, I can get up to an 11 by 11. Because every time I do another 3 by 3 convolution, I grow the effective, what we call the receptive field of this effective kernel by 2. Starts at 3 by 3, then 5 by 5, 7 by 7, 9 by 9, 11 by 11. So after doing 5 convolutional layers of size 3 by 3, that I can get up to essentially doing like one 11 by 11 convolution. Is that kind of making sense? Okay, so, and the size of my final kernel, that's the receptive field, that kind of tells me like how big of a window it has to work with, what kind of things it can do in spatial filtering. The larger that is, the more flexibility it has to come up with different shapes and represent like different shapes that it sees in the input. So, okay, but now let's talk about putting in the activations in between. If I consider, let's say, these two systems. So the top one, I do convolution followed by ReLU. The bottom one, I do convolution, ReLU, convolution, ReLU. Make a little ReLU shape. Okay, which of these do you think is going to be more powerful? In terms of what kind of patterns it can detect, what kind of stuff it can do? Bottom one, right? That's what we saw when we went from like linear classification, which is essentially represented by this, to something like this, two-layer network, where all of a sudden you can do nonlinear classification if classification is your objective. So, so that's kind of the point, is that like if you have like a budget, like you say, I want to have a receptive field of size 11 by 11, yeah, you can do that with one big 11 by 11 convolution and then a ReLU. But if you say instead, well, I'm going to make that 11 by 11 out of 3 by 3s, and then I may as well just put in the ReLU in between because that's a pretty simple operation, doesn't really cost much. You get something that's way more powerful than that one linear layer and nonlinear layer. You get something that's much more effective. So basically, this allowed them to get a much more powerful network than they had with AlexNet. So this is one of the big advances. Just focus on small kernels. Don't ever use big kernels. Okay. So is that idea making sense? Okay. And there were various depths that they played with, VGG 11, 13, 16, 19. For some reason, I think 16 is the one that I hear most about. It's the one that achieved the top 5 error rate of 7.5%, which was twice as good as what AlexNet got. Okay, so that's pretty cool. And it remains a respected network today. Like I said, when they did this MRI study, they actually looked at a bunch of different feature encoders, to say, how do we construct those features? And VGG actually did a lot better than Inception v3, which we'll talk about, which is one of the standard ones they use to evaluate GANs and stuff. So there is a difference between them, and some of them might work better for some applications than others. But yeah, VGG is still used today, even though it's quite old by now. Yes?
Sorry, you just mentioned the word encoder. What do you mean by
Oh,
that?
how did, sorry. I don't remember how I used it. Maybe I shouldn't have used it.
Yeah, I don't know. I heard it and it kind of threw me.
You referenced it in terms of GANs.
So I guess what I meant was the feature generator. It's like you're taking an image and you're encoding it as a set of features that you will then process with some algorithm that measures quality. I think that's probably how I meant it. And I don't know if we haven't talked about GANs. GANs are ways to generate, to sort of dream up things like faces or whatever you want. And then there you have a similar question, like if I have this system that can dream up random faces, how do I measure the quality of those faces? And so they do something very similar there. They put the original training faces and then new fake faces they generated through something like VGG or Inception, and then they measure like various statistics in this new feature space, and that's how they do it. So this is kind of a very well-used approach, is to take one of these early neural networks that was originally trained as a classification network, but then they use it in a completely different way. They use the convolutional features in a completely different way. Okay, so all right, so just a few things about the depth. So as you can see, it's deeper than AlexNet. I'm trying to remember I think AlexNet was maybe like 7 layers. Can't remember exactly how many. And now we're talking about maybe double that. Also, the number of parameters is 3 times AlexNet. So things are getting more complicated. Things are getting deeper. Okay, any questions on VGG? Okay. So then, basically what you saw happening from 2012 to 2014, performance is getting better, networks are getting deeper. And so basically this was what people realized at the time. Depth is really key. We got to make things as deep as possible. But if you just sort of naively make networks deeper, the parameters just start exploding. So as you go from AlexNet to BGG, you're going from 60 million to 180 million parameters, and it's just getting out of hand. Like they just, if they want to go twice as deep, like can they handle 360 million? No, they can't. So, so they said, well, how do we do depth with efficiency? So that was what they did at Google, and that's where this GoogleNet, also known as Inception v1, came out of. The name Inception is kind of a meme from film Inception that happened in 2010. And so basically what they were able to do, and there's several versions of Inception, so this is the very first, they were able to come up with a network, GoogleNet, that used only 5 million parameters, which is huge reduction, right, compared to 60 or 180 million. And in fact, it did even a little bit better than VGG, 6.7 instead of 7.5. So they really were successful. And so it's deeper, 22 layers instead of 16 or whatever. And one of the advances here were Inception modules. Okay. So deep, much more efficient is the key here. So Inception modules kind of work like this. So we tend to think of, this is, let's say, the features, the tensor of features from the previous layer. And we tend to think of doing something like a 3x3 and then getting some new features. But they're saying what you can actually do here is in parallel to a 3x3, you can do a 5x5 and another 3x3, but maybe followed by max pooling, and in parallel a 1x1. And then you stack all the outputs side by side in a new tensor. So it's kind of like a more free way of doing convolution where you're not constrained to just use one kernel size. You can actually use a combination of kernel sizes and other things. And this ends up being just much more efficient than just using the one kernel size. So that was one of the main things. And in particular, when you use a bigger kernel, you use fewer channels. Because remember that the number, if you think about like the number of parameters associated with this guy here, you have to count not only size 3x3, but how many output channels you're making, right? Because the total number of parameters is number of input channels times kernel size times number of output channels. So number of input channels is the same for all these different guys. So what really matters here is if I have a really big kernel here, maybe I should use fewer output channels to keep the total number of parameters in check. Is that making sense?
What's the purpose of the 1x1 convolution in this one?
I don't know. I guess it just being there is somehow helpful. So, 1x1 convolution is, similar to a matrix multiply, you could say, because there's no spatial processing, but there is still processing across channels. So if I just think of like, I have, let's say, n input channels and m output channels. If I'm doing 1x1 convolutions, I'm really just doing a matrix multiply from input channels to output channels, where I'm doing the same thing at every pixel. So it is something that is used once in a while in these networks, and here's one example. So somehow it helps to do this. It's just an extra thing, and as you can see, it probably doesn't cost you much in terms of parameters. Right? Each one is just one number. So yeah, so that's what they did. And some of the arguments for this is that when you have kernels of different sizes, you can do this pattern matching sort of simultaneously at different scales. Like you can look for really tiny features as well as bigger features simultaneously instead of always looking for features of a certain size when you're at a certain layer. So that's the idea behind scale invariant. And if you want to learn more, there's a nice overview of everything they did. They did more than just this, but everything is talked about in here. Okay, so that's GoogleNet. Any questions on that one? Okay. All right, so residual networks. So this was a huge advance. So basically, when you look at what happened through 2015, all the winning networks were just getting deeper and deeper and deeper. And so, is there a limit to this? Yes. They basically found that, we talked about one issue, which was vanishing gradients. So vanishing gradients, when people were working in the old days, they couldn't figure out how to make their networks deep because their gradients were vanishing. And then they said, oh, we can do ReLU and batch norm and things like this, and that helped a lot. But then, once things were getting into the 20s of layers, they started to notice other weird things happening. Like basically as the networks were getting deeper, the training error was increasing. So it's like somehow when they added new layers, it was like causing the networks to do things that you don't want. It was like preventing them from doing what you want. And this is a little weird. You would hope that if I add a layer, at least things don't get worse. Maybe things stay the same. Because maybe if I add a layer and I have a vanishing gradient, that means that layer just won't really do much. It won't be learned, but it won't hurt you necessarily. But here, as they added more layers, things just got worse and worse, even while training. And this was called the degradation problem. And so one kind of way to think about what's happening here is that the typical way that we construct these layers, which is like convolution followed by a ReLU, it's difficult to make that operation behave like an identity function, like a function that just passes the input without any problem. Because if I had functions that could act like identities, layers that could act like identities, then I could stack a new one on without worrying about it ruining anything, right? Because in the worst case, it just acts like an identity, doesn't do anything bad, doesn't do anything good, but doesn't do anything bad. And so this is sort of one way to think about why, when you add these new layers on, they were hurting things, because they can't act like identities. Because if you think about a make, it doesn't want to just pass things. It wants to clip off what's negative. So the idea was maybe we can make layers act more like identities. And okay, so difficult to make layers act like an identity. Okay, so the idea that they came up with was called the skip layer, the skip connection. So it was something like this. So if you have, there's different ways to do this, but like in this case, you have a convolutional layer, linear layer, ReLU, and another linear, let's say conv layer. And this thing we said is difficult to make act like an identity. But if I have this there, that means that this whole thing can act like an identity if I just set the weights to 0, right? Because then this gets blocked and then all the data flows through here. So just by adding these skip connections, all of a sudden you can make things act like identities, which means if it's not useful for this to do anything, it's very easy to learn zeros here. It takes it out of the picture. But if it's useful to somehow use it, you will learn weights there that are helpful. That's one way to think about these. And these things are called residual blocks. These blocks where you have some non-trivial stuff with a skip connection around it. Okay. Now, in some cases, it's a little complicated because maybe you add downsampling here. So that would mean that the dimension, the number of, the size of the image or feature map coming out of here is actually different than the one here, which you're trying to add it to. So you can't just do a simple addition. So what you might do is you might learn a dense layer that just does that basically does something like subsample this so that it matches this in size. So there's various tricks to handle dimension changes. Okay, so this idea came out with the ResNet in December 2015, and this was a huge advantage. It actually allowed networks to get into the hundreds or in fact even thousands of layers depth. You know, went from like people stopping at like 20 something to being able to really have no limit in some sense. I mean, the limit comes with memory and computation and things like that, not with depth as like some difficult thing to do. So, so this won the contest in 2015 with a 3.6% error rate, and just for reference, GoogleNet, you know, it's twice as good as GoogleNet roughly. So that was a big advance. And had slightly lower complexity than BGG 16, although still, you know, pretty complex network. I can't remember which depth was the winner, but like I said, there's ResNets of various depths available to you pre-trained in PyTorch. Okay, so any questions on the idea? Yeah.
When you say complexity, what, in general, what we're looking at? Because the number of layers are larger.
You could talk about complexity in terms of number of parameters, and you can talk about it in terms of like computations like multiplies, and they're probably going to be pretty linked, right? If I double my parameters, I probably have to do twice as many multiplies, and multiplies occur in the forward pass as well as the backward pass. So that's kind of what I mean, roughly speaking, complexity. Some operations are more complicated than others, like multiplies are usually more complicated than an addition, so typically you count multiplies, but you know, roughly speaking, things grow. Complexity typically grows with the number of parameters in more or less linear sense. Okay, yes?
I have a question. So as the depth of neural network gets bigger, so when you load the trained neural network, depending on different applications, is the loading time be degrading as the depth of neural network?
It's not so much about the depth, but the total number of parameters. Like some of these networks are very deep, but per layer they don't have that many parameters. Other networks are shallower, but they have a huge number of parameters per layer. So it's not about depth, but more the number of parameters. And yeah, probably if you have a lot of parameters and you load it, it takes more time. If you push data through it, there's more multiplies, so that takes more time. So all those things are an issue, especially once you start talking about mobile devices, like you want to do something on your phone or something even simpler.
Yeah.
These things matter. So we'll talk about that in a moment. But at this point in the evolution of deep networks, people were more focused on like pushing the performance limit without so many computational constraints. They were focused on like, what can you do on a computer versus what you can do on a phone. But, yeah.
I mean, in that regard, though, really, isn't the big concern just training? I mean, once the network is trained, then it doesn't seem like it would require that much computation power to, run it. Right?
That's right. Relatively speaking, inference complexity is way, way less than training. But still, like if I have a really simple device, I'm memory limited, I'm compute limited. So even just loading it on my device, like an Arduino or whatever it is, right? Loading it there, having the memory to store it, to process it, it still matters. So yeah, but you're right. Training is something that you can only do in a data center, but then we can all load these things onto a laptop and play with them. That's not a problem. They're pretty fast to play with. Okay, good questions. Any other questions? Okay. Okay, so but there's actually another way to think about ResNets which really explains much more what's going on. So the idea is, let's say this is just a rough sketch of a 3-layer ResNet. And so you have some sort of processing block here with a skip connection. And then you have another one here with another skip connection and so on. And so when you look at this, you notice that there's 8 different ways the data can flow through this network. Like one way is it can go through all the skip connections. Another way is it can go through the first module and then the other skip connections and so on, right? And because for every layer there's 2 possibilities, you get 2 times 2 times 2 possibilities for how data can flow. So in general, when you have L layers, you have 2 to the L possibilities of how data can flow through the network. And this is another way to think about this, where you just unravel those, in this case, 8 possibilities, and you just show them in parallel. So like, here's the path that goes through all the skip connections, here's the path that goes through F1, and then the other skip connections. And in total, you have 1, 2, 3, 4, 5, 6, 7, 8 different ways you can go through the network. These are just a different view of what's happening. Now, when you look at what happens when L is large, there's this binomial distribution, and you can count like how many of these layers will be length 1 or depth 1, how many will be depth 2, how many will be depth 3. And what you notice is that most paths are depth L over 2 when you have L layers, especially when L is large. You can already see this happening. Well, I guess we can't really see it happening in this simple case of 3 layers, but yeah, once you get to like 100 layers, there's 2 to the 100 different paths. But when you look at the number, there's a single path that is all skips, which is nothing compared to 2 to the 100. And there's a single path which goes through all, and that's nothing, and so on. There's like L paths that go through a single one. So you can see that maybe most paths are going to be about L over 2 in length. That's what it turns out to be. And there's another thing, which is when you think about the longer paths, because of all the reasons we talked about, there's basically a reduction in the gradient as you go through. It's not as bad as if you would use a sigmoid or something, but even with a ReLU, anytime the data is negative, it's 0, it has to be positive to get a gradient through. So basically, when you have these depth 100 networks and you look at how much gradient actually flows through that 100 depth path through the network, it's very little. And so as a result, when you take into account the number of paths of a given length and the fact that longer ones aren't really that helpful, you find that, for example, in a 110 layer network, the only paths where they're really meaningful, the data really meaningfully goes through, have lengths between 10 and 34. They did this whole study in this paper, and they figured that out. So in some sense, like, even though there's, in theory, 2 to the 100 paths, there's actually far fewer of them that are really meaningful, and they all tend to have these lengths. And in some sense, you can think of this overall ResNet as really an ensemble or a collection of these different networks in parallel, where you have some things shared across those networks, but they're all a little bit different, but they're all a little bit similar, or they're all connected to other ones. So this was the view, a different view of ResNets, where you thought of them as an ensemble or a collection of many other networks working in parallel. And with this view, this is kind of gives a window to understand why they're working so well. As we'll talk about in the next unit when we study ensemble methods, these ensemble methods are just simple ways to get a lot of, let's say, we call weak learners, weak predictors, to come together to do something that's much more powerful than any of them individually could do. So essentially that was the explanation that was provided by this paper, and that's pretty much taken to be kind of the real understanding of what's going on at these ResNets. They're really ensembles of shallower networks. And that leads to a lot of other nice interpretations. For example, there's a connection to dropout in the sense that, let's say if I have a network like this, and if I just completely remove this guy, well, it doesn't kill the network because the data can still flow around it, right? In some sense, what it does is it gets rid of half of these paths. They're gone, but then I still have other paths here. So similar to how in dropout we dropped out nodes in a network, now we can drop out layers, drop out a whole layer, which in some sense drops out some paths in this overall ensemble. And so this is called a deep network with stochastic depth, because as you randomly drop out these layers, you're essentially randomly changing the depth of the network. And this really can help speed up ResNet training and reduce overfitting and so on. So, so it's a useful view of what's going on with these ResNets. Okay, any questions on ResNets? Pretty good? Okay. All right, so that was kind of a flavor of a few of them. And there ends up being a whole bunch of these other Inception networks that every version had some new advances, more efficient Inception modules, auxiliary outputs where there was like, instead of just looking at a loss at the end of the network, you would take these auxiliary outputs out of the middle and do some sort of losses on them. There's all these different things that they came up with, and you can read about them if you're interested here. And there was like a ResNet version of Inception. And like Inception v3 is a pretty famous network that took second place in 2015. And this is one of them that is still used quite a bit as a feature generator. So as I mentioned with GANs, when you want to say, is this GAN like generating really high quality outputs, often you look at the features in this coming out of Inception v3, and you look at how good they are. And there's something called FID, Frechet Inception Distance, which is exactly that idea. So those are things that happen. Like I said, you can read about them more. Another idea that came out in 2016 was a DenseNet. And the DenseNet is similar to a ResNet, except that in a ResNet, the idea is this layer is connected only to its previous one, this only to its previous one. In a DenseNet, you have this connected not only to its previous one, but all previous ones. And then this one is connected to its previous one and also all of its previous ones. And so you have all these connections. And you don't do this necessarily for 100 layers. You have like a dense block of maybe 4 or 6, or I can't remember 8 how many they do, but you have all these connected together, and you have concatenation of those dense blocks. And essentially what they found, they engineered this to work well and outperform the ResNet a bit. But there's some issues with memory. It's kind of very memory hungry when you have to do the computation graph for this. There's so many paths, and it's tough for the frameworks to really allocate all the memory for all the paths. So I haven't seen these used as much as ResNets today. Some people use them, but ResNets are still super famous. Anyway, after this point, people stopped worrying as much about making these networks better because they were already getting really good. They thought, what we actually need to do is really make them more efficient so we can use them with mobile implementations. So memory limited. So SqueezeNet was one of the early ones in this direction. It achieved AlexNet-like performance, but had 50 times fewer parameters. So that was a big advance. Another one the next year, MobileNet, even better. Very efficient in memory and computation, but much better than AlexNet. AlexNet is not great, especially compared to later things. So this one did a lot better than SqueezeNet and so on. And of course, the story doesn't end in 2017. Things kept happening. They keep adding more things to PyTorch. So PyTorch has all the ones that I listed here, but it has other ones as well. And I haven't checked lately exactly which new things were added, but there are more things. So that's kind of just where I'm going to stop in terms of bringing you through the evolution of deep networks. There's tons more we could talk about, but just due to limited time, I'm going to stop here. Any questions on any of this stuff? Okay. So let's talk now about how we can play with this stuff in PyTorch. So Torch Vision models, Torch Vision is what has all these pre-trained things. So Torch Vision models is where you can find the models. And so there you can find VGG16. And when you download it, you can download it pre-trained, or if you want to train it yourself, you can do that too. You can download it without the weights. Anyway, if you print the model, then you can see exactly how it's constructed. So VGG basically has 3 different sections. It has a features section, feature generator, which is, there you see all the convolutional layers, 2D convolutions. You also see ReLUs, of course. You see max pooling in 2D and so on. Then you have a classifier section, that's at the end. There you find your linear layers, so these are your dense layers, just your matrix multiplies. So you have, in this case, 3 of those. You also find dropout with 0.5 probability, and you have ReLUs. And in between, so feature layers, classifier, in between, you have this interesting thing, which is the average pool layer. So let me try to explain what that is. So, as you know, in convolution, I specify the kernel size, right? That kernel can be applied to an image of any size. I could apply it to a gigantic image, a small image, a wide image, a tall image, doesn't matter. I can do convolution with any image size. But eventually, once I get to the dense layers, my first dense layer is going to have a fixed input size. It's like a matrix. I've trained it. I can't change that dimension. So somehow, if you want to use this network with images other than 224 by 224, you have to figure out a way of adjusting the size that are output by the convolutional layers and get it to match your dense layers. I have to get it to exactly 25088. And so this number, 25088, this guy is 512 by 7 by 7. And this is because, let's go back to the picture. Here we go. This is VGG. This is what we're talking about. So we're talking about here. So these are my dense layers. This is my, right, and then this is these are my features, my convolution layers. So this is where I have to do a transition from something that is, you could say, roughly speaking, has an image space to something that no longer has any pixels at all. It's just a list of numbers. So the first, I do this flattening where I'm going to take this tensor and I'm going to ravel that into something of size 25088. Okay, so what that adaptive average pooling layer does is no matter what size image you put in, it will make sure, using average pooling, which is just averaging over pixel regions, it will make sure that the output is 7 by 7 spatially, and by construction there's 512 channels. Okay, so if you put in a bigger image, it's going to average over little sections of it to reduce it down to 7 by 7 here. If it's a smaller image, I think it probably interpolates it up to 7 by 7. So no matter what image you give it, it will always be 7 by 7. The features will be 7 by 7 spatially at that point in the network. And that way you know that it is guaranteed to match the size of that first dense layer. Okay. All right. Okay. Any questions on this? All right. So you see there's this nice output. You can see exactly how every convolutional layer was constructed, number of input channels, number of output channels, what's the kernel size. The stride, this is basically the subsampling. If it had a stride of 2, then it would be subsampling by 2. The padding is how you specify whether it's a valid mode or, what do we call the other ones? Full? Yeah. So with a 3 by 3 kernel, if you zero pad by 1 row of blank pixels, then it's valid mode. So you just have to specify how much padding you do relative to the kernel size to get what you want. Yeah, okay. So, all right, so let's talk about, well, I think this is a good place to stop. We'll go through this demo more on Monday and show how we can load images and how we build the code to do all this stuff. All right, so as I sent an announcement today, Friday in a week, you guys have your second midterm. So you can bring in 2 sheets of paper. So you can bring in the one from your first midterm and you can make a new one. Any other questions on the midterm? Similar in spirit to the first one. I'll try to make it a little bit easier. The first one was you know, more difficult. The average was lower than I was hoping that it usually, and lower than it usually is. So I'll try to make it not as difficult, but otherwise similar in spirit. So let me know if you have any questions. Have a good weekend.